Welcome to the Royal Astronomical Society of Canada May meeting. It's a very long name. It's just the Astronomy Club. Any members of the public here?
Green chemistry and observing, as far as I can tell, and all kinds of wonderful astrophotographs to drool over. But first, I'd like to announce that Al Seaman has been awarded the RASC National Service Award. This award's going to be presented to him at the GA this year, but we get to announce it here. Al Seaman got this award for his many, many years of service on mailing lists and council meetings, and probably most people know about the fact that he's done an enormous amount of work maintaining the observatory. Al Seaman is passing that job on to Brian Black. Brian, are you here? There's Brian Black. Wave. People who have keys to the FLO observatory or want to get keys should talk to Brian at the end of the meeting. He'll tell you about the fees. And I'd just like to point out that not every observatory has Al Seaman and Brian Black to take care of it. Some people have problems with damp basements. Just like to point out that this is an important job and we appreciate the work. This is the Glenlee Observatory from the RASC Winnipeg, the Red River flooding.
And can I mention, Attila, the report from there was that there were no reports of Somali pirate attacks.
Thank goodness.
All right, to start the real part of the meeting, we have Tim Cole to explain to us what we can see in the sky this month.
Thank you. Well, we have a nice opportunity for Mercury for a change. Now, there's a little bit of mythology out there that claims Mercury is really hard to see. It actually isn't. It's actually not too difficult, though from the city it can be a little bit tricky because it's. Where the heck is my microphone?
Hi. Welcome to the fabulous grey room. Now, yeah, there's a big urban myth that Mercury is really difficult to see, but it actually isn't too bad. It's just that it tends to be kind of low. So you get your best opportunity for it when you happen to be fairly near something to act as a reference. And here we happen to have it nicely near the Pleiades. Alas, you're not likely to see it quite this dark. I had to cheat a little, but so coming up tomorrow is a great opportunity to catch it. Mercury right now is a nice little crescent, so it should be lots of nice fun to enjoy if you can see it through the clouds. Saturn is absolutely spectacular at the moment. If you haven't had a chance to see it yet, enjoy it when you can. The rings are starting to open. I really thought the rings at the crossing would be really, really dull and boring, but it turns out to be really quite nice in its own way, and it's a great opportunity to catch the moons. So, perfect opportunity and enjoy. Here's your crack at moons. This was just, actually this is plotted for tomorrow, we think. And we've got a transit of Tethys coming up. Should be lots of fun. Now we're actually getting Tethys and its little shadow. So nice opportunity. And this big whoop, Jupiter is at its brightest. Jupiter's always bright, and you have to be up at a ridiculous hour in the morning to see it. But if you happen to be really, really masochistic, here is your chance to see Jupiter at its brightest.
What time of day?
Like early freaking morning, like 0400, like dark 100, like in the dawn. Now, if you're like me and you stay up all night, it works. If you actually get up in the morning, well, don't tell me about it. And just by luck, all the Galilean moons, appropriate since this is our year of astronomy, the 400th anniversary of Galileo reporting on those moons, nice opportunity for you. Allegedly, you can tell them apart by color, but in the early morning light, fat chance. And by sheer luck, the great red spot, which is now roughly salmon colored, should be visible for you, which means it probably won't be, but there you have it. And I have just brought up Richard's bit because I completely screwed the pooch. At any rate, I shall now disappear and pass this over to somebody else.
Yay. Yes, applaud when I leave. Sure.
Okay, I'll be. Good evening, folks. First of all, I'll be talking about the stellar death, about stars with medium or low mass sizes, not the big ones, the hefty ones, or the very small ones. So as we begin, there are objects in the universe that have an evolutionary tale to tell, and stars are no exception. They all go through their stages of birth, midlife, and death. Our own star, the Sun, is now in its midlife crisis at 4.5 billion years, with about another 6 billion years to go before it starts to expire. It will remain on the main sequence branch of the HR diagram for about another 5 billion years before its supply of hydrogen begin to run out. According to theory has it that stars having masses of up to 8 solar or thereabouts will undergo the same evolutionary fate as our Sun. In fact, only decades ago, and I didn't even know this, it was a popular myth that all stars in the universe ended their lives in a cataclysmic explosion. And tools such as the Hubble Space Telescope confirmed that this was simply not the case. And of those that are the most massive, 95% will in fact go supernova. Next please. Okay, so what we'll be doing tonight is we're going to be talking about stars right along this fork here. This is not the galaxy fork. These are the small brown stars, the red dwarfs that gradually shrink into the brown dwarfs and eventually black dwarfs, but I believe none have been found so far. And the high mass stars, the real hefty ones here that go supernova, and of course the fork subdivides into either a neutron star, a black hole, and maybe something in between, which is called a quark star, which is another relatively new object. But we won't be talking about that tonight. Now, the planetaries as an object are very popular with astronomers. First of all, they provide a crucial link between a red giant's final gasps and a cooling white dwarf. Planetaries can also be used as standard candles to determine the size and age of the universe, another tool for astronomers, and also tracking the speed or velocity of planetary nebulae in their host galaxies can yield the distribution of dark matter in these galaxies. Could also be an indicator for dark matter as well, although we don't know what dark matter is. And they can also yield the chemical evolution of galaxies through a process called nucleosynthesis. Now, for us amateur astronomers, they are beautiful to look at and can be also a challenge object as well. Canadian planetary guru, Dr. Sun Kwok, he's at the University of Calgary, says that 95% thereabouts of all stars will undergo a quieter death. So, which may explain why we may be overdue for a supernova explosion, at least in our galaxy. There have been about 2,500 planetaries catalogued. However, their overall galactic population is expected to be about 10 times greater. Planetaries are extremely difficult to see because of their small angular sizes, distances, and the intervening dust and gas. And because of their optical nature, precise distances to these objects are usually difficult to obtain. And they are studied pretty well in practically every wavelength along the electromagnetic spectrum, including optical, radio, infrared, and even in the X-ray section. But there are aspects of planetaries that remained poorly understood. One of them being their beautiful shapes and structures. They have so many tantalizing shapes that are nice to look at through telescopes. And now, how do they end up that way? What is the mechanism that dictates their outward flow of gases into the interstellar medium? Next, please. In the optical, there are 3 basic shapes. As you can see here, these are all different examples of planetaries here, and the rough shapes, and you see the arrows pointing on the outflow of gases, and also by their evolutionary hierarchy as they get older. These are, I believe these here are the young ones, and as they get older, they progress down, and these are the different shapes: round, elliptical, and a butterfly. These are basically symptomatic diagrams of the outward gas flows, and of course the central star here, which will become a degenerate white dwarf. And here are the actual photographs, and these are the simplified diagrams. And here too, there's a bit of a That was a little bit of a schematic here about the different shells within a planetary nebula. Now, as I said, there are three shapes, the round, elliptical, and butterfly, and the evolutionary pattern as well can dictate their shapes. So there are so many of them in the galaxy. When astronomers look at any one particular planetary, they're looking at one particular aspect in one time segment. So they are looking at basically like a time window to see these things. Next, please. Here are 4 examples of different planetary. This is a young, intermediate, and this is already getting older in their age, a few thousand years. Actually, this one here is a few thousand years old. They were all taken at, you have to note here that they're all 7,000 light years away. It was taken by Hubble in February of 2007 with the WIFPEC camera. And as you can see, the outward gas is getting larger and larger, and there's some knots of nitrogen gas, which is sort of pinkish here, left over. There's mostly nitrogen in the earlier stages, and then there's oxygen and hydrogen as the green and blue as the gas shell starts to expand. Now, of course, there's a lot of different shapes, and one aspect about planetaries is astronomers don't know how to explain or come to answers as far as the outward moving of gases due to magnetohydrodynamic forces, but that's for another topic of discussion. Now, what is happening here is that these sun-like stars are depleting their fuel supply when they start turning into the pre-planetary nebula stage, and then begin to cast off shells of gas that we see in these spectacular images. The concentric rings around the planetary contain puff of material ejected by the star in its dying phase. So when a star is beginning to puff up material, like for instance Betelgeuse is starting to, but it should become a supernova, astronomers know that a planetary or a star is nearing its final years. Now, the puffs provide evidence that the star is aging and facing certain death. After this stage, the star wraps itself in a cocoon. Meanwhile, the planetary cannot be seen through optical telescopes. Infrared and other wavelengths have to be studied. We don't yet see it in our amateur scopes as yet. And this makes it difficult for observations in optical wavelengths. So, like I said, the astronomers have to trace a planetary star's footsteps back in time, or at least the star, the dying star, by several hundred years to understand the ultimate fate of a medium mass star. Next, please. Here's one planetary where you could see the concentric rings thrown off in its earlier stages when it was a red giant. There's the white dwarf starting, and these are the complex rings within the planetary, which are very hard to explain why they take on these beautiful shapes. And these are the gases that were expelled or belched out by the giant before it went into the planetary stage. And these are the bipolar jets here, which can be explained by a binary companion, although it's only theory. Next, please. Now, this one is self-explanatory here. I'll let you read the images here. It is the star's core, I call it its heart, that initiates the dying process. What happens first, that it begins to morph into a lump of carbon about the size of Earth, or about 12,000 kilometers. Hydrogen has been depleted, and helium fusion begins to take over. The stars that are destined to become planetary nebulae, carbon is the ultimate fusion byproduct. It cannot go into heavier elements beyond that. There simply is not enough mass above the core to continue the fusion into the heavier elements, such as potassium, calcium, and ultimately iron. Those are for the heavier mass stars. So because heat cannot be replenished, the star within a star begins to cool like an ember. Meanwhile, the layers above continue to generate the thermonuclear fusion. That's where the heat still is left. So 2 shells are produced around the star. One is helium burning and one is hydrogen, which is the outer shell. The helium is on the inside. The gravity there continues to compress hydrogen and helium, but only for a short time. This is where all the action is going on. Meanwhile, below, nothing is really left there for anything to happen. As an example, helium fusion rates are extremely sensitive. a 2% rise in temperatures can more than double the reaction rate as far as the evolution, as the death process goes. And as a consequence, the star becomes highly unstable. Next, please. Here we have a rough schematic. The core here, this is the bloated red giant. So basically you have a star within a star, the outer older star dying, and you've got the process of another star being born within. There's your helium shell, your hydrogen shell a little bit further, and of course you've got your distended layer of gas and dust on your bloated red giant. Carbon in the star's atmosphere begins to settle, and in doing so adds mass to the inert carbon core. The problem here is that whatever fuel remains lies too far away from the core. So there is not enough mass above it to compress it to ignite this thermonuclear bomb. The helium burning layer quickly expands and cools, and the star then takes on a reddish cast. The reaction rates, of course, begin to diminish or subside. So what happens next? Well, the final spasmodic fits of helium fusion does a type of a belching act by ejecting the star's outer envelope into the interstellar medium. Each spasmodic fit creates a bubble of gas having an escape velocity that is equal to our fastest probes, or about 36,000 miles per hour, which is slow in terms of cosmic. Next, please. Here's another schematic here. You got the white dwarf here, the distended red giant, the outward slow gas puffing out of the star, and you've got the faster, hotter gas coming out from the very hot core of the white dwarf. And this is sort of a bow shock or a membrane, a shell. Eventually this will protrude, this will break open, and the contents will catch up with the slower, earlier gases which were belched out earlier in the life of a star, and this will empty the contents into the interstellar medium to create new stars, planets, and perhaps even eventually people. Now, the final helium flash creates a dense and highly organized spray of gas and fresh dust particles. Next, please. As we see here in the Retina Nebula, there's the star, and there's the dark alleyways or veins of dark material caused by the helium flash. And of course, you've got your major axis bipolar flows, which astronomers don't completely understand. The helium flash forms the dust lanes and bright lobes along the major axis. And about 1% of this new dust mixes with the ISM, or interstellar medium, and begins to reflect light from the dying star. Next, please. Here too is a similar star, NGC 7027 in Cygnus, with dark lanes and of course bipolar nebulae, bipolar gases. And of course each nebulae is slightly different. There are thousands of shapes literally, and that's what makes it very interesting for us to try to pick them out in our spokes. The immediate area around the planetary nebula becomes enriched with carbon and silicon-rich particles. That is the main elements around these objects. One of the reasons why astronomers enjoy studying these objects is that they determine the chemical evolution of galaxies and the prospects of life elsewhere through nucleosynthesis. Next, please. And along the HR diagram, well, simplified, this is where our sun is right about here. It'll track roughly here and make sort of a meandering hairpin turn in this area here, becoming a red giant starting to swell up. There's going to be the helium flash shortly in this area here, come back and come back out here again. That's when the hydrogen burning has been depleted along the HR diagram, and then it starts to burn helium in this section. Next, please. Here's a more detailed view. You got the main sequence right here, the white dwarfs, the red giants, the hot, big, luminous blue variables, the helium flash forming the dust lanes and another evolutionary part of the planetary phase. And of course, you can see it sort of meanders back and forth into the asymptotic giant branch, which is the AGB. And I think this is the red giant branch here. The giant star becomes unstable and variable, much like a Mira-type variable, so it starts to pulsate. These pulsatings give rise to the ejections of gas from the dying star. Now, the time spans for a planetary nebulae are about 10,000 years. So astronomers must really capitalize on these fleeting moments of cosmic opportunity. After several thousands of years, the cloud expands and then disperses into the intergalactic interstellar medium. Next, please. And this is a white dwarf in NGC 2440 in Puppis. And as you can see, the nebula is beginning to disperse, become very tenuous, and you get a very hot white dwarf in the center of the star. This is more in the later stages here. So what remains is a cooling white dwarf. But before the star has a chance to cool, it will heat up to at least 100,000 Kelvin as it continues to shrink. The collisions between the electrons in a white dwarf will halt further collapse into a smaller object such as a neutron star or a black hole. So the electrons then stabilize at a certain point, and then the star remains at that shape, which is about 12,000 kilometers in diameter. It could not go any further. So it's all a question of the movement of the electrons. Now in this image here, the star at the center burns at about 200,000 degrees Celsius. The ultraviolet light begins to fluoresce the surrounding medium, and when the gases disperse enough, allowing the light to shine through, this is when amateurs can see them as these colorful planetaries, because prior to that, in the pre-planetary stage, we don't really have a chance to see them unless you have a very large telescope with special filters. Next, please. And this is a simplified map, spectral map of a planetary nebula. The predominant line of hydrogen alpha, which gives it their sort of hot pink look in photographs, and hydrogen, the O2, O3 here, doubly ionized oxygen, which is also going on in around the planetary nebula. And there's one note here that the strong line in the green part was originally called nebulium, historically, by William Huggins during the mid-1800s. And it was Henry Norris Russell and Ejnar Hertzsprung, the inventors of the HR diagram, that proposed that the green line was due to gases at very low densities, gases that were extremely rarefied. So nebulium was kind of shot out the window, and that was the explanation for that. Next, please. Here's an image, another spectral image of NGC 2437, and there's a planetary within that open cluster. And again, you got your spikes here, hydrogen alpha, doubly ionized oxygen. And these interrogation spikes here are probably due to light pollution. So the guy wasn't sure, the author wasn't sure whether it was really the light from the planetary or whether it was a nuisance from extraneous light variables. And of course, you've got your line here, your electromagnetic spectrum there of the different colors to correspond to the spikes here. And of course, the height is the strength of the line. Next, please. M57. What we are looking at here is probably down a long tube that is about 1 trillion kilometers long. So really, it's not a true planetary in the sense that it's just a ring or a shell on a star. And of course, you see the outside looks like a flower here of earlier gases that were puffed out by the red giant earlier in its dying stages. And of course, you can see a galaxy here that starts to come out. And there's the white dwarf. And there's the cavity created by the outrushing gases. The gases plow into the slower medium here, into the slower gas, and starts to ionize and turn hot. So you see it's starting to glow. And the gases break that barrier, and then the gases start to it punches a hole into this bubble, and all the gases disperse into the ISM.
Richard, just for scale, how would the solar system look like in there? Would it be a tiny dot? Or
it would be a tiny, microscopic, like a virus. Because I believe this, here, from here to here, not from here to here, it's about 1 light year across. So that's, we can't really. Could I add this question here? Yeah, okay, sure.
You said it was a cylinder, so is it just fortunate that we happen to be looking down the cylinder? That it could be rotated, we would see it from the side?
Yeah, because of our vantage point, like if we were in another part of our galaxy, we might see it as a long tube with bipolar flows, but we're looking down the throat. So that's a theory that there's another part beyond that, so we're looking straight down. It's like galaxies. And next, please. We have 2 more slides, I believe, here. Oh, no, another one here, bipolar flows, and of course, hydromagnetic flows, which are very difficult to explain right now. But you got the central star. Well, it doesn't work. Anyway, the central star is in the middle, and the bulb is on the floor. So, next, please. Oh, well. Yeah, okay. Now, this is the forecast of the sun. It looks rather gloomy, sort of say. Our sun has a main sequence on the top left. The sun has a bloated red giant. In about 5 billion years, it'll go to a giant. Well, there goes another piece here. I'm falling apart here. Anyway, that's the sun as it goes into a red giant. Hopefully we won't be around or have migrated to another planet, because it will swallow Mars and perhaps even Jupiter, and it would be nice to see this from far away but not up close. So anyway. So we know about a fair deal about the stellar evolution of medium and low mass stars, their birth life and their dying years, but when scientists start to grapple with their complex shapes and energies of mass ejection, things begin to get a little bit murky. Stellar mergers and magnetohydrodynamic models can be a starting point. Magnetohydrodynamic referring to the flow of electricity, magnetic flows along lines of gas, but not to falling objects here. Stellar mergers at this point of understanding are still difficult to understand, but more work needs to be done as far as mapping this distribution of debris around the central star and learning more about the complex magnetic fields found along these planetary nebulae. So when Messier first discovered M27 in 1764, little did he know that with his new observation of his, he would in fact be opening up a new can of worms, as we can see right here. So, okay, I'll just pick up my stuff and...
One more slide.
One more slide? Okay, there's another slide. Oh, that's sort of the end slide. That's artist's depiction of what might happen to Earth in 5 billion years. So eventually, before the cold comes, the hot will come, and then the sun will shrink as a white dwarf, and we'll see it as a very small pinpoint of light, and Earth will be a barren, frozen wasteland. So there is the all lived happily ever after the end. So that's it.
Excellent. Okay, and now for something completely different. Richard. Now, I also appreciate the physics going into that. I'm a physics teacher, and I spend most of my time going through physics like that. I do like calculus, and in fact, I'm a very left brain kind of person. But tonight what I'd like to talk about is something on the other side of things. I'd like to think about taking the time to lay back and just observe. So, being a left brain kind of person, I do a lot of mathematics. I teach my students about calculus. I try and show them the names of the things, and I try to show them the physics behind what they're seeing. And for fun, what's this one?
A laser pointer.
Does this not work? Yeah, this one's okay. And in fact, I've been known to solve killer Sudoku just for fun. That's the kind of person I am. But it's not the only thing to astronomy. It's not the only thing to my life. And I think we had a perfect example of that at the start of our International Year of Astronomy, when Tafel Music gave us that excellent presentation, I hope you were all there to see it, of the music of the spheres, the art and the beauty of the night sky. And this is a different side of human nature. It's a different side of all of us that we should try and make use of and appreciate some of the beauties and the joy of the night sky. This presentation that Tafel Music gave a whole different aspect to the subject of astronomy, the music, the poetry, the philosophy behind astronomy. And I think that's an important parts of our lives as well. Now, several years ago, I spent a summer trying to get in touch with the artistic side of things, and I'd really like to recommend this particular book. For me, it was a great inspiration. Drawing on the Right Side of the Brain by Betty Edwards, and she's an artist who tries to teach all kinds of people how to use the artistic side of themselves and how to make use of the right side of the brain. Now, this may not be entirely scientifically correct, but I think there is some very strong basis in that you do have two different sides to your ways of thinking. It is actually physically associated with the sides of your brain. The left side is generally associated with naming things, with language, with scientific analysis, with mathematics. The right side of your brain tends to be more creative, more spatially oriented, more associated with spatial perception, and sometimes with more of the emotional aspects of things. And using this book, I found that I could actually feel a switch taking place. That when you're using the left side of your brain, and I think many of us do this, we seem to be carrying on a little conversation all the time with ourselves. There's words going through our heads. We're constantly talking to ourselves. We're naming things. We're describing what's going on. And it's all making use of just one aspect of our brain. And that's what happens in many of our star parties. We're standing there, and that's me in the middle there, doing my usual job of pointing things out in the night sky, telling them the names, answering questions, because people are curious. What's that up there? What's it called? Where did it come from? And like our previous presentation, all the different physical details about what's happening, what causes it, what the shapes are, and this kind of thing. So that's one way of looking at the universe. But, you know, sometimes we should do that. Stop the talking. Just lay back, look up at the sky, and appreciate it. Now, part of the exercises in the book gives you opportunities to try and exercise this method of just looking. Unfortunately, when we see familiar things, we tend to name them, and then we replace them in our head with a standard picture. And that kind of gets in the way of noticing anything new. Once we've seen it, named it, it's a picture. We've got that in our head now. It really helps, and one of the exercises that Betty Edwards suggests is turn it upside down. Look at it from a different point of view. Forget about what constellation that is. Just appreciate the shapes. It's hard to do if you're seeing things that you're familiar with. And once again, a personal experience has changed my way of looking at things. I've gone to different countries at different latitudes, and I've looked up at the sky from a different place on Earth. And especially when you go down towards the southern hemisphere, the northern constellations are upside down. And that does give you a chance to see them with new eyes and to appreciate some new shapes and pictures. In fact, one of the things I found I did when I looked up at some very familiar constellations from a different point of view, I invented a new constellation. I found a new constellation I'd never seen before. That red one in the middle. It seemed very obvious to me. But when I tried looking it up on a star map, it wasn't there. It turned out that I'd made a new constellation from part of Draco and part of Hercules. It's my diamond in the sky. Now, people who are unfamiliar with all our constellations will often do this immediately and they're for fun. I also teach grade 9 astronomy, and last semester I was trying to encourage my students to take a look at the night sky, and because I was only doing it during the day, I had to take some pictures and show them in the classroom. So I showed one of my not very good pictures from the experimental farm looking towards the north in Ottawa, and showed them that picture. And said, what constellation is that? And of course, these grade 9 students, not being familiar with our standard names for constellations, said, it's the shopping cart. And I sort of looked at that and I said, well, you know, you're right. what is this dipper thing? I don't have a dipper that looks like that. If you're British, maybe you have a plow that looks like that. But these days, why not call it the shopping cart? And actually, it's a good way of introducing people to astronomy. Sometimes they feel a little bit overwhelmed by all those Greek myths and the things that they don't really see there in the sky. It's really not that important. What's important is just getting to know your way around and recognize that the same shapes are always in the same kind of relationship with each other. So if you want to call it the shopping cart, or the diamond in the sky, or whatever, let it happen. Now, observing the night sky is also good for amateur astronomers who are going into a bit more depth. And appreciating those shapes is also a way of helping us find our way around star maps and using the telescope. A few years ago, I made up a web page like this. It's still available on our RASC Ottawa Centre website. And it's called A Star Hop Through Sagata. And one of the things that when I'm doing star hopping with is that I'm looking for shapes. I'm trying to find a shape on the map, a shape on the map that matches what I'm actually seeing in my finder scope to see if I can find my way to a particular object. Now, if you talk about this, if you try and label it with words, as I've said earlier, you're going to start replacing the real things with a standard, something that's really not completely there. But the shapes that you're seeing on the map here are not standard shapes. They are the patterns that are the patterns that are there. And so it's actually better to turn off that internal dialogue and try to just look for there it is. Now, I hope I haven't distracted you by using the laser pointer, but that's the kind of thing that I'm doing at the telescope. Not talking, not naming anything, but just trying to find my way through the patterns of the night sky. So I'll just leave you with one last picture. This is another thing that was unfamiliar to me. Looking into the southern hemisphere and seeing a whole new set of stars that I'd never seen before, I wasn't familiar with, and I didn't know any of their names. But they're beautiful, aren't they? Thank you very much.
Well, hi everyone, Mike Moghadam here. You're going to see me twice tonight. What I'd like to do is, next slide please, is talk briefly about one of the big IYA, Ottawa Centre IYA events that is coming up very shortly, Saturday, June the 6th. Now, I know you've heard me talk about this before in previous meetings. This is an event that we went through a process and applied for and so forth. And it's a fairly prominent event. Other centres are doing this. In fact, I think only six groups across Canada, 6 or 7 groups across Canada are doing this. So I feel quite privileged that we're offering this as well. So we are able to, in this program here, we're able to attract a fairly prominent speaker, this fellow, Dr. Roberto Abraham from the U of T, and he's going to be delivering a talk on titled Cosmic Dawn and Monster Telescopes. And in this talk, he's going to explore how, with new telescopes and technologies, we can peek back to the beginnings of the first light, or the moments right after the first light of when the universe was created. So this is an event that we're planning to be held at Carleton University in the Bell Theatre, I believe. And it's an event as I said, on Saturday, June the 6th, where it'll run at from approximately 1 o'clock till 5 o'clock. And I say approximately because I'll give you the exact details, and we're just in the final stages of that right now of the event. But when it'll begin and when it'll end. But what we're planning is that we'll have we're planning on having a series of introductions. Dr. Abraham will speak. We'll have, I'm actually planning as well to have, you may remember about a couple of monthly meetings ago, we had Rob Alexander and Penelope Goranson deliver their astronomy, that lovely astronomy song. We're planning on having them do that again to the audience, sharing that to the audience, as well as a variety of displays and solar observing and meteorite displays and so forth. So this is an event that we plan on promoting fairly heavily, and should be a lot of fun. So you'll be hearing more about that. Next slide. I get a lot of emails and from various groups that have got wind of International Year of Astronomy, and one group called the Cube Gallery. That's in the Parkdale area. They approached us and said, "Look, we've got an event which we call a Nocturne. In this gallery, it's they have a series of a variety of showings of paintings and sculptures and so forth. And they host a number of theme nights, including it spans everything from musical groups and dance groups and to traditional gallery type of offerings." And what they did is they registered an event with IYA and IYA Canada, and what they have is they have a series of artists that have come up with some paintings of the night sky and astronomy scenes, and they've asked us if we can participate in a couple of their events. I think there's a slide. So actually, they have 3 events. Basically, their events run from about the end of May to the end of June, and they're planning a kickoff on May the 22nd. On June the 4th, Rob Dick is giving a light pollution talk, and on June, it doesn't show on the slide, but on June the 11th. They're also planning a star party with telescopes and so forth to go along with their showing and so forth. So this is a pretty creative gallery. I had mixed feelings about this at first, but in speaking to this fellow here, he seems to be. It interests me because, like Taffla music, we can reach out to sort of the non-traditional audiences. People who might not be normally sort of acquainted. Made up counter astronomy or the kinds of interests that we all have here tonight. So sounds pretty interesting. I think that's it. So more later. Oh, one thing, I wanted to thank Attila and Chris for helping me out with the slides tonight. I really needed their help, and they really came through. Thank you.
Thank you, Mike. We're going to have a short break.
Give it to Chris and then it's all done. Okay. Many of you are familiar with the fact that over the last few years I've made a number of presentations about the geology of the inner planets, the outer planets and their moons and so on, using two-dimensional PowerPoint. And I thought maybe this year, especially given that it is the International Year of Astronomy, how about we actually go 3D, actually 4D because we're moving through time, and actually do a series of fly-throughs of various parts of the solar system. There's nothing actually to beat being there, but this is about as close as I can do for you. I use a program called Seeker. It's by a Software Beast. No, I have absolutely no financial interest in Software Beast whatsoever. It's similar to a program which you can see for free and use for free on the internet called Celestia. The big difference, as far as I can tell, is that in this particular case, instead of actually doing the whole thing by hand, you can actually program. And in programming, you can get just what you want and then reproduce it. And that's what I'm going to do with you tonight. This is the second of these movies that I put together. The one I did just before Christmas, I think, was on the rocky planets, the inner planets. The metaphor of the way Seeker works is you're in a spaceship. And that spaceship, of course, is moving around in the solar system. Space is big, which means that we don't have the time to sit here and wait for the spaceship to actually get from A to B. So I have to speed time up. As we're moving around in 3 dimensions at the same time, orientation tends to get a little screwy. I realize that one of the earlier talks suggested, forget orientation, forget labels, just go with the flow. But the reality is that often as Earthlings, when we're looking at something in the solar system, we're used to seeing it a certain way. So you'll see during the movie that if we do get ourselves out of orientation, I get the spaceship to correct ourselves back to an orientation which you and I are more used to actually seeing things in. So as I say, I've already done the rocky planets, and we launched for that rocky planets tour through the solar system from Pluto. Tonight I'm going to do a part of the outer solar system. We're going to look at Jupiter, which is very appropriate given that it is a 400th anniversary of Galileo this year, and Saturn, and a selection of the moons around those 2 gas giants. As last time, I'm going to focus on actually walking you through the planetary component and the moon component. And in the background, you'll see the galaxy, and you'll see various constellations. Some of them I may actually spot, but please, I'm looking for audience participation. If you see an obvious galaxy in the background, an obvious constellation in the background there, and I haven't called it out to orient people, please jump in. The more audience participation, the better. So, let me get myself started up here. Okay.
You ready now? Or?
Yeah, ready to go now. Chris, there we go. And all I'm going to do here is I'm going to tell it this one here is what I want. And we're in business. Okay, so here we are. We're out here at Mars. Oh, by the way, the rumbling you can hear, this is the ship's engines. There's no sound in space, so here we are. This is the Martian jumping off point for our trip to the outer solar system. And we'll have a quick look at Mars before we leave, of course. Actually, let's just position ourselves. There, of course, is the outer solar system. This is where we're actually heading off to, Saturn and Jupiter. And here's an exploded component of the inner solar system. There's Mars. That's where we are right now. Earth, Mercury, Venus, Sun. And that's where we're out to. So we'll just do a quick tour here around in standard orbit around Mars. You can see one of the moons coming around. There we go. There's Phobos. Deimos will come into view very shortly. You can see the surface features of Mars here quite nicely. There's the Martian Valley, Valley Marineris. Here are the famous volcanoes, the 3 of them there on Tharsis Plateau. There is the biggest volcano or mountain in the solar system. And we're setting course for Jupiter. Off we go. There's Corvus, and you can see it's the right way up. By the way, it was pointed out to me the last talk that Software Beast had the Milky Way the wrong way around. I wrote to them and told them this. They were extraordinarily embarrassed. And when I told them that I was going to be giving you a presentation here, they immediately corrected it and sent me the patch. So here's Jupiter. And of course, as I say, we've accelerated time. Here, of course, is the Milky Way. We've accelerated time, so we're approaching. All these names here, of course, are the names of various moons, because otherwise we'll get lost and we won't be able to see them all. And you can already tell, because there's the ecliptic, well, we've already gotten ourselves out of orientation. So what I'm doing here, we're correcting the ship's equatorial attitude. There's the red spot, or the salmon spot, if you prefer. Watch carefully on the surface here. You will actually see shadows of moons as they come by. So we're here watching Jupiter itself rotating. There's the Milky Way. We're going to take a quick look at what the sun looks like from way out here in the solar system. There's Ganymede. There are the Pleiades. There's Taurus. We're the right way up here. There. That's the sun. That is what is illuminating what you see through your telescopes when you ooh and ah to what you can see on Jupiter. So we're coming back here to Jupiter. I think it's quite, and what we're going into polar orbit here. I think you're going to see a moon shadow here very, very shortly, if I remember correctly. We're going into polar orbit so that we can better see the disposition of, there we go, there's the lunar shadow. Just so we can see the Jovian moon system more clearly. We're pulling back now. And you can see that there are a number of moons in here which you're not used to seeing. There's Io, which you can clearly see with your own amateur telescopes. Here's Europa. As I say, there are other moons which are in closer, but we don't usually get too much of a peek at those unless you've got a really nice big telescope. Here comes Ganymede. And we're waiting for one more, which will be coming in from up around here. And I think you'll probably guess which one that one's going to be. There she is. There's Callisto. And you can see now the disposition of the moons that we actually look at, but instead of seeing them going back and forth in a linear fashion, as we often see from our telescopes, you actually see them from above. So we're going to set course for Europa and take a look at it. There's Europa, zeroing in on it. You'll see Jupiter popping in and out of the image here at various times, because time is still running. Even once we actually get to Europa and hover over it, we'll still be orbiting Jupiter. So here we are coming in on Europa. And you'll see that it's not necessarily the full moon we're seeing. We're going to bring ourselves around to the daylight side so we can better see the features. You see these fractures here. This, of course, is an ice moon, extremely smooth, very, very few impact craters on here, so a very young surface, very dynamic. And it's quite well illustrated here. You can see the fractures which are characteristic of the moon, and these chaotic areas here where the fractures are actually being reworked by modern ice volcanism on the moon. There's the Pleiades. You can see now getting a nice crescent moon as we pull back. There are the other moons, and so you can see that's actually the ecliptic plane. Here again is Taurus, so we're approximately the right way up as far as Earthlings are concerned. So let's pop off, and there's the sun, by the way. And so we'll pop off and we'll have a look at Ganymede. There's Jupiter. Of course, we're seeing the dark side because the sun was on the other side. This really is in 3D. There's Ganymede down there. And you can see it looks fairly dark. You'll see it. I can't recall actually just how dark it is as we get in closer. I'm intentionally allowing time to run through here so one really gets a sense of the size of space. So the sun is obviously to our right and probably just behind us. And you can see on Ganymede here the characteristic feature, again, an icy moon, two kinds of ice, this dark, older ice, and this lighter colored, younger ice. And you can tell it's younger because there are huge veins, hundreds of kilometers in length, of the white ice that cuts into the gray ice. And here we are pulling by in a flyby. We can now see the daylight side, night side, and the terminator between. And these white patches here represent impacts and ejecta from those impacts. Similar to the kind of thing you'd see on a rocky planet, except that this is the geology of ice. So we'll set our sights on Callisto. Callisto is a very, very different moon in the sense that its surface is so much older. It really looks as though not much has happened to Callisto since its formation after the great bombardment that it was affected by. Here's interesting. There's the Pleiades. There's Taurus, and it's clearly the wrong way around. And look at this. Here's Orion. There's the belt of Orion, clearly on its side. We're clearly not sort of the right way up here. Here's Callisto, and you can see the name, but you can't see much else. And this is because the sun is on the other side of us, and what we're actually going to be seeing is Callisto's dark side, the night side. There is Callisto right there. Here we are. We're zooming in on it. There's Venus, by the way, just to the side. It's about to get eclipsed. So we're looking at the dark side here. We'll come around in standard orbit into the daylight side so we can actually see what the surface looks like. What I had to do, by the way, in order to make sure that I could repeat this, I had to pick a time and make sure that, in fact, the simulation kept running with the same time. And in fact, the time I'd picked was last April. Here's the surface of Callisto, extremely old, pockmarked. No new ice seems to have come out on there, at least not at any large scale. These are really old features, at least 3.5, 4 billion years old. So here again, we're going by in an elliptical flyby here, the daylight side, the terminator, and onto the night side. Good job those engines are still running, because we wouldn't want to actually sort of run out of gas out here. So there's the Milky Way, and we're going to set our course now for Io. As we come towards Io, you'll see Jupiter come back into the picture, because it is rather close. And in fact, it's that close that there are a number of moons there. There's Jupiter with the moons coming around. There's the ecliptic plane, so again, we're at an angle. But there are so many moons out here that I've actually had to turn the moon labels off. That, I think, is Io, if I remember rightly. And you'll see it come across Jupiter's surface, and you will, there's Io, and there's its shadow. There's Io, we're coming into Io now. Io, of course, is very different from the other moons of Jupiter. Instead of being an icy moon, this one actually is a rocky moon. And it is the most volcanically active feature in the whole of the solar system. All of these pustular blips that you can see here and these rings, these are the results of volcanism. We're coming down to the daylight side so you can see this better. But here, for example, there's a nice volcano there. I can't remember the name, but it's got a ring of ash around the outside. There's a beautiful one there. There's the volcano dark. There's actually the lava field. And this is the ash which has come up and been deposited around it, and you'll see just coming up on the horizon here. Here is the largest volcano, active volcano, by the way, on Io today. There she is with a beautiful red ring of ash, and the reason that red ring is there is that Io has no atmosphere. So as the ash comes out of the volcano, it comes out on a ballistic trajectory, and therefore it forms like an umbrella of ash, which all falls to the ground at the same distance from the volcano itself. Here are more, these dark things here, these are actually lava pools. Here comes Jupiter, it's trying to elbow in on the action. We're doing a flyby here as we actually leave Io in the daylight side, the dark side, and the terminator. There again, the Pleiades, and we'll see how we're doing for way up. Probably at about 45 degrees, I would think, to the ecliptic. Oh no, actually, we're not bad. There's Jupiter kind of trying to work its way in again. What's going to happen between these two here, both looking as crescent shapes? And it turns out that, in fact, Io is closer to us. And the sun, of course, is over on this side and behind the screen. And here we come into the dark side of Jupiter. So swinging around here and getting our bearings, getting ready to move on. There's Uranus down there. There's Europa coming around. There was another moon up here. So thereabouts is the ecliptic. And we're going to set course for Saturn. Saturn, of course, is going to be a long way away. Yes, I have sped up time even further here. There is Saturn. We just lost everything. No, because my screen's live here.
There's text flowing in that box.
I know.
Your computer's so bad.
Oh dearie me! You know, I think we may have blown this one. Hang on, let me just try something here. I think we just landed us in the black hole. Black hole.
Simon, is the Fitzgerald contraction?
Oh no! I'm. Hang on, but let me just try that one again and see what I can do. See if I can recover from this.
Is that a spaceship or is it transport?
Oh dear, no. No, I'm afraid, folks, I've blown it on this, or at least my computer's blown it on this one. I don't think we're going to see the rest of this one here. So I'm going to have to apologize, and I have to present you. No, it's. I've never seen this happen. I have no idea why it's doing this at all. Oh, hang on. Let me just see if I can recover this.
Ran out of gas.
Ran out of gas. Hang on. Hang on.
We'll never get home.
No, I'm sorry. No, we've lost it. I'm afraid I'll have to bring you Saturn another time in a shorty. But I guess we got hit there by the ghost of Galileo, who decided he only wanted us to actually show you Jupiter, and that was going to be it. All righty.
I think that was great.
Simon?
Yes.
Maybe you could pass on another little tidbit to the Visp boys. And this is, the way they represent the sun at any distance, it is vastly underwhelming compared to what it really would be.
Mm-hmm.
Because here, from Jupiter, we're only about 5 astronomical units away. So the sun is about 1/25th its brightness, but it would still be much brighter than -20 magnitude, whereas on screen, it's a little dot, similar in size to about a 0 magnitude star.
Yeah.
So it's orders of magnitude underrepresented. It needs to be brightened up. Maybe tell them to put a big kind of a glowing halo around it to.
I'll pass that along to them. What they've actually done here, I think that they've intended this to actually be the intermediate version to a more spectacular version. I mean, on this one, for example, you can't stop and start it once it starts running. You can while you're putting it together, but once you actually run the finished simulation, you can't actually stop and start it, and surely a fully finished package would allow you to do this. And so I think that they certainly are interested in upgrades. They got working very quickly when they realized they'd actually flipped the Milky Way around, mirror imaged it. Mind you, I still had to remind them after 3 months. And I said to them, it was only about 3 or 4 weeks ago, and I said, you better let me have another version of this, because otherwise the RASC is going to see yet another boo-boo. Unfortunately, this is not due to the flipped Milky Way. I have no idea why this suddenly happened. I've never seen this one happen to me before. It's got to be something to do with the graphics card. All righty, folks, next time.
Thank you very much, Simon.
Okay, you can put the first guy. Okay, Deep Sky Challenge, we're going to be in constellation Canis Venatici. We're going to look, it's almost straight overhead, around declination's around 32 or 33, so basically it's right overhead. We're going to look at this one, and this is called the Whale, for obvious reasons, okay? This one is called the Hockey Stick, or the Crowbar. Okay, so we're playing NHL tonight, okay? We have the Whalers from Hartford, and we have a hockey stick, so we're gonna do this. These are basically both spiral galaxies, edge-on. So edge-on means we're looking at the side of it. This is a companion galaxy, so the NGC number of this is 4631. This is 4627. This is 4656, and this is a little companion, 4657. This was discovered by William Herschel in 1787. Some information on it. It's a really bright galaxy, visual magnitude 9.8. Surface brightness is pretty good, 13.3, and its angular is 15 by 2 or 15 by 3. So this is basically about a quarter degree, which is pretty large. The field of view here is less than a degree. So you got two beautiful, this is another, two beautiful galaxies in the same optical field, both edge-ons. This one is the hockey stick. It's another edge-on spiral. This was 25 million light years. This is 30 million light years away. Brightness 11, so this is about a magnitude fainter than this one, and it's about 9 by 2. Some distortion here. So basically this is an interacting system that has happened somewhere presently or in the past. This is having a lot of action going on here. We've got a lot of hydrogen regions, which are these red things, and I believe there's some nitrogen else going on there too, and this is actually gravitationally, this whole system is gravitationally together, interacting. There's a couple other, so these are our, what you're trying to try and do is locate them and try and pick out some detail. This will show up as mottling in a larger telescope. The elliptical, there's not much detail here, and the idea with this one is to try and see the little bend right in here. And you can see some of the distortion coming off here. Oh, we'll go to the next slide. There's some, now you got a big scope. We're gonna look at, so these are our two here. There's our 13th. Now there's another, we can go to the next one. Okay, there's actually a couple galaxies. This is the PGC 15th. There's one here, and there's another one right there, and that is for your PGC 2832 120, and I couldn't get any information on the magnitude, but I think it's probably, if this is 15, that looks a little fainter. This is like maybe 16 or 17. There is also another one right here, and that's a PGC 1987306, and that's 17th magnitude, so I don't know if we're going to be able to see that one. And there's another one down here somewhere, right there, a little tiny one, and that's magnitude 17.7. That has another PGC is another catalog. So this one, these two are easily visible in an 8-inch scope, no problem. Getting to around maybe a 12 magnitude, we should try and hunt these two guys down. So the challenge is really locate these guys, use them as your landmarks, and follow this little chain here. Goes ding, 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 bang. There you are, and come across this way. So there's our little guideline, like Richard was talking, to look at the flow of the patterns, and it's pretty easy. There's a pretty bright star, just go right along, and then it's right beside these two stars. So let's let this be our challenge for next month. Okay, that's it for the Deep Sky Challenge. One more thing, I just want to show you a book here. I'm going to turn the lights up just for a second. Great book. I bumped into Sue French 2 years ago at NEAF, and this was made in Germany only by Oculum, and she was really pushing to get this made in English. So it has come out by Cambridge University Press. It's called The Atlas of the Messier Objects. It's the best Messier book there is, bar none. It took all of them put together. Kramer's book, Walter Scott Houston stuff, Robert Glyn Jones from England, all put into one. Fantastic book, 400 pages. The color illustrations are amazing. $46 or $47 through Amazon. It's a steal. Okay, highly, highly recommended. Thank you.
Yeah. Okay, next we're going to have people showing us the observations and astrophotographs they've taken. Slide, please. These are people. First is Paul. I believe Paul likes to speak from the comfort of his chair.
That's okay, you can hear me. It says there Chernik 7, right? Well, that's not Chernik 7. Next one, please. There's Chernik 7 over there. And what I was showing you is that group of stars on the right. So that just tells you, I've been in astronomy 65 years. I got shelves and shelves of sky atlases, programs in the computer, all kinds of catalogs, and $20,000 worth of equipment, and you make mistakes. So I tell the young ones that are starting out now, when you come to these remote type of obscure objects like Chernik 7, nobody, unless you're Reverend Evans down there in Australia, he seems to know the shape of everything, you will make mistakes. Easy enough to do it. Hubble called IC 1275 a galaxy. An IC 1275 is a globular cluster. So even if Hubble makes mistakes, don't feel bad. Keep taking pictures. It's very difficult. If you have a small field of view, that's only 17 minutes across and about 12 minutes top to bottom. So don't be afraid to take pictures. Everybody makes mistakes. Check all your photographs later. I found that this was an error. But it's possible for anybody. You won't make mistakes on M42 or something like that. But when you get to these remote objects, these UGCs or these Lunds or Cherniks, you don't know the shape of all of them. And like myself, I made a mistake. So don't worry about making mistakes. Everybody makes mistakes. Keep taking photographs.
Thank you, Paul. I agree. I once discovered what I call the Great Antenna Nebula. It was this wonderful 3-degree long, very low contrast, just really visible, elliptically shaped haze. And I asked my friend, hey, have you seen this before? He says, looking at the antenna there, he pointed out a microwave radiator on an antenna that I happened to be pointing my 25-inch at, which is saying, the more equipment that you have, the more likely you are to screw up.
More spectacularly.
Yeah, it's another fun aspect of the hobby. Okay, next is Brian McCulloch. Brian?
Okay, I see we've reversed the image, which makes it look very nice. It's not as blinding. Thank you for that, Chris. On April 23rd, my wife Bridget and I went to the Sci-Fi Spectacular at the National Arts Centre. So it was all the music of Star Wars and Close Encounters of the Third Kind, Star Trek. It was fantastic. A couple of the segments were narrated by George Takei, of course, who was Mr. Sulu in the original Star Trek series. So we waited after the concert, figuring he would come out to sign autographs. Well, at the end, everybody had thinned out and still no George Takei. So I talked to one of the NAC employees. It turns out it was Daphne Burt, the director of musical programming there. And I asked her, and she said, oh, no, he was on a red eye coming into Ottawa from California, been doing media all day long, and he's already gone back to his hotel. And I thought, oh. So anyway, she saw I was holding a book in my hand, and it was George Takei's autobiography. I had actually read this thing a couple of years ago, had a read of it, and tossed it into the Salvation Army. When we found out we had tickets for this event last week, I went prowling the Salvation Army again, and what did I find? I found a copy of the book, not the same one. So this is the book I had in my hand, and she said, oh, were you hoping to get it autographed, I guess, eh? I said, yeah, but I said, well, that's okay, though. I said, even if there had been a huge long lineup, like I'm not an autograph hound, it just would have been fun. And if there had been a kid in the lineup, I probably would have given it away to the kid if it was a huge lineup. She goes, oh, that's nice of you. She said, would you like me to ask Mr. Takei? He's here until Saturday. Would you like me to ask him to autograph that for you? I said, oh, that's probably going a step too far. But she goes, no, I'd be happy to do that. So I said, okay. So I said, are you interested in astronomy at all? So she said, well, actually, I am. So I said, I'll bring you a package of astronomy materials. So we met on the Monday afterward, and she had left the book for me, signed. It was autographed right on the cover to Brian McCullough. Galactic Greetings, George Takei. Right. So I had left her a package contained a couple of Sky News magazines, some little meteorite fragments that Ron St. Martin has been giving me for doing some of the outreach programs. So I think it was a nice exchange, and everybody went away feeling very good about it. On the 23rd, when I came home from the concert, it was perfectly clear out. So I thought, well, moon's not in the sky. What am I going to do now, right? So there's a couple of porch lights on in the back, but I thought, you know what, it's like 11:30 or whatever it is. I went into the observatory, and I was quite tired, and I thought, I'm just going to go do a bit of galaxy hunting in Virgo. So there's my little quickie sketch of M58, one of the brighter galaxies, 9.8 magnitude in Virgo. But the story that goes along with it makes it memorable for me.
Thank you, Brian. Gordon?
Okay, last month's lunar challenge was to find the cross of death in Lacus Mortis. And while I was, I did some observing, and I found what looked like the right area, and I also happened to find a couple of photographs that I had taken. This was in March 3rd, and the Lacus Mortis region is up in here, I think. And that's next. This really bad resolution. It's the same photograph, just enlarged. But if you look, when this comes up on the website, if you look at it in the smaller version, you can actually see there's a dark cross right here. Okay? And there's also, I found 3 of them. There's another one, a white one here. I have sketches of those 2 I'll show you in a second. And there's also a third one. There appears to be a third one that looks like a lobe there, a lobe there, a lobe there, and a lobe there with sort of a white circle in the middle. So, did I? Which one was it? Was it the third one? Yep. Oh, that's disappointing. That's the one I didn't do a sketch of. Anyway, so there's my sketch of the upper one. And this is a Borg down here. Okay. And then my third one, or second one rather, has Borg there in the center. And the white cross is there. Turns out the real one is over here.
Hey, that's all right.
Okay. No, that's true.
Thank you,
But
Rick.
it's fun trying.
So, anyway, this winter in February, I lugged the telescope down to the Winter Star Party, and Attila and I spent, I don't know, a couple of hours collimating this thing, and then the wind blew so hard that I couldn't use it. So it was really discouraging that way. So anyway, I threw it in the back of my trailer and bounced it all the way home. And then I tried to collimate it again this last night, or the night before, I'm sorry. And as far as I could tell, it was still in collimation. I didn't dare touch any knobs. And this was my very first image with a collimated scope. And the seeing was terrible, but it's quite a scope. Anyway, thank you very much.
Thank you, Bob.
Oh, I need to make another comment. As a presenter, I find it very discouraging when Simon's half talks are twice as good as the rest of ours full talks. I did this last night. I wanted to get it off to Attila. I didn't have any time to do any research, so I looked in Starry Night, which has a kind of a pathetic galaxy catalog, and I labeled a few of them. Can you go to the next one here now? So here's a few of the big ones that you can see. Now this is actually 4 pictures. My telescope has an extremely narrow field of view, and so this is 4 images stitched together in a mosaic for me to get this much of the sky at one blow. And this is a little tiny bit of the, probably a quarter of the observing challenge that we were supposed to do. I ran out of time. It was getting late. Okay, next image. All right. I have, it seems like 20 or 30 images of M51. It's my favorite galaxy to image. And last fall, Peter Cerevolo loaned me a telescope that was his proof of concept of a telescope that he's selling now. And if you have, an extra 25 grand, you can buy this telescope from him. It's a fantastic imaging scope. I've seen some images done by it now. It's just incredible. This is his proof of concept. So I think there's 3 levels between this one and the one he's selling. And I took an image of M51 last fall with it and sent it to him. And I got back quite a quick email from him telling me that I hadn't collimated the telescope very well, except it was Peter, so he worded it differently. So anyway, this winter in February, I lugged the telescope down to the Winter Star Party, and Attila and I spent, I don't know, a couple of hours collimating this thing. And then the wind blew so hard that I couldn't use it. So it was really discouraging that way. So anyway, I threw it in the back of my trailer and bounced it all the way home. And then I tried to collimate it again this last night, or the night before, I'm sorry. And as far as I could tell, it was still in collimation. I didn't dare touch any knobs. And this was my very first image with a collimated scope. And the seeing was terrible, but it's quite a scope. Anyway, thank you very much.
Thank you, Bob.
Oh, I need to make another comment. As a presenter, I find it very discouraging when Simon's half talks are twice as good as the rest of ours full talks.
Sanjeev does have her last name, but I try to avoid pronouncing it.
Thanks. Okay, just want to show you a few more images with my DSLR. I use a Canon 40D. This was March 22nd at FLO. I wanted to catch a couple of winter objects before they were gone. So this is the Horsehead area. You'll probably recognize that as one of the belt stars of Orion. This was done with an 85mm refractor, and they were all, I think I stacked about 30 90-second exposures. They're all unguided. So this field is about 2 degrees wide. The camera, it's a stock DSLR, so it doesn't have, it has a standard IR cutoff filter in it, so you might see a little bit more red here, but so it's a bit more muted. But this is the Pleiades. Again, I wanted to try this before I lost the chance for the season. So this was again March 22nd at FLO, and this is also unguided. The same setup. I used my refractor, and I stacked about 30 90-second frames. This was just about a week ago at a dark site about 15 minutes west of On Prior. The seeing wasn't very good. This is actually imaged at 1800 millimeters using an 8-inch scope. This was guided it's about 4 minute. I stacked about 3-4 minute exposures. Of course, it's M13. Again, I don't think the seeing really supported that focal length. And this is M57 again at 1800 millimeters. It's a bit soft. But you might be wondering why I went straight from the winter objects to the summer objects. And that's because the mount that I'm using is giving me a bit of a hard time, and it must be a balance issue, but it won't track properly past the meridian. So I'm missing all the juicy stuff for the spring. So basically I have to go after the rising objects. So here I am at 3 a.m. Imaging the summer objects as opposed to spending the later part of the evening imaging the spring objects. So that's something that I'm working on right now. Thanks.
Thank you, Sanjeev.
Okay, thanks. I'm being facetious here. I don't know if I should use the laser pointer because everything I touch breaks. We don't know. There are things about gravity we still don't know about. It's not my fault. Okay, I'm also a club member, president with my wife, co-president of a small club in Alexandria called the Glengarry Stargazers.
And one of the things we do is that we invite guests once in a while, low profile, high profile guests from here too as well. And this time I figured, well, I'll get someone from the Canadian Space Agency. I got a few guests from McGill University and from other areas, from other institutions. The idea about getting a guest came again at 2 o'clock in the morning, coming from Tim Hortons on my way home from work on a lonely country road when I saw the banner of Marc Garneau for an election for the Soulanges-Vaudreuil election several years ago. But of course, Marc is not with the Canadian Space Agency, but he's now in politics. So I figured I'd get someone from the Space Agency, and believe you me, it's really twisting arms and elbows and everything you can get your hands on. First of all, well, the club, our club has about 10 members, and getting someone from the CSA was definitely no easy task. A lot of phone calls, a lot of emails, and with the newspapers, with the CSA themselves, and as well as with our membership to make sure everything goes well. The main thing into organizing this is you got to keep a lot of communication going. You've got to keep some people on a short leash, so things are kept, organized and nothing goes out of whack. But in the end, it all came out quite nice. Next. That's the marquee outside the Best Western in Cornwall. They did a nice little favor for us by putting the welcome sign for Tara outside. It was a pouring rainy day the day before on Saturday, I believe, and there's just some of the people inside the conference room at the Best Western. I figured on getting an astronaut on first, but astronauts are very hard to get. They're all going on space missions. We were going to get Julie Payette, but she was unavailable at that time. And also, as well, advertising can be a little bit expensive. So if you do something like that, make sure you've got some money in the budget for advertising. Make sure that you relay the communication properly, because they have a tendency to jumble words up a bit and could be very frustrating. First of all, about Tara. Next, please. I don't know what we have here. Oh, there's our club there. You might notice one guy there in the back, Gary Susik. He's a member. He's a spy also. And that's basically our club. And Tara is there right in the middle there. And that was at the inn, the conference center downstairs at the restaurant. We took a picture before. A lot of newspaper media there as well. So a little bit about Tara. She's also a little dedicated athlete, so she loves doing sports here, especially in the Ottawa area and the South Shore. She is a manager for the ISS, the International Space Station, Dexter, Canada Arm 2, and she's a project supervisor. What is it, April? What's her official title? Real-time manager for all of the above. An extremely busy person. And in fact, she missed the buffet. We had invited her for the buffet, but she missed it on account of her running activities here in Ottawa. She was also a graduate at the University of Western Ontario. We did mention to Tara that we would like to have her again, but she was a little bit, I guess, not pulling in that direction, because she would rather do it again herself, but she didn't suggest any other members at CSA, because she was, according to her, she was treated like a queen, and she would love to do the thing all over again. We all had a lot of fun, and it's really, in the end, it's really worth it. She basically mentioned about Canada's involvement with the International Space Station. Next, please. These are the models that she has on loan. She had to sign them out in blood, because a lot of the astronauts working on upcoming missions, they borrow that same set of Lego blocks over there. And but actually, it's quite the thing. I don't know. It's made out of wood, and someone had handcrafted, hand painted them. It was really a work of art. That stuff there. You can't buy them in any hobby shop there. So as you can see, there's the banner there that I created there for Tara. She actually was so excited, she took it to her office to show all the people at the staff, and a lot of people wondering where she got this, and they wanted to do the talks themselves, but Tara says, no, the talks are for me, myself, and I, and that's it. So she didn't want anybody else in the space agency to come to our club and for them to do our talks. So I don't know if that's real or not. As a matter of fact, she actually invited us for a VIP tour in a few weeks from now. But unfortunately, they can only take 8 or 9 people because for security measures. In a way, like I said, it was really great. Next, please. I don't know, more slides. So that's the newspaper article. Is that the last slide? That's the newspaper article with Tara. They did a very good write-up and very enthusiastic, very good, bubbly, high-spirited speaker. Maybe I'll manage to get her here one day. Who knows? Even as part of an audience. So if you're doing anything like this, just be organized. It took us about a year to prepare the whole thing. A year in about 1 hour. It's just like getting together a wedding. You know, you spend 6 months to a year, and everything is over in one night. So.
I got that recorded there.
Yeah. Okay.
How true.
Anyway, it came out quite by accident. So. This wasn't planned. So if you want to talk to me about it later, I guess. No, not about. No, we didn't talk about that either. So anyway, that's all. That's it.
Folks, since I blew it on Saturn, I asked Attila if I could make it up to you in about 3 minutes here with a quick improv. You probably saw in the newspaper today, there's certainly those of you that saw the Citizen, that NASA has come out with a new press release on its messenger mission to Mercury. And what the newspaper, of course, is focusing in on is the fact that they've managed to find yet another large multi-ring basin. It's all very exciting. It's called Rembrandt. But the really exciting thing, if you get a hold of the actual press release, it's a 2-page press release. It's practically the last line. Those of you that remember my Rocky Planets talks will remember that Mercury is a very peculiar planet. It's made of a core of iron nickel, which is what all rocky planets have. They have an outer part too. On Earth it's called a crust, and then there's a stuff in between called the mantle. The thing is that Mercury, of all the rocky planets, proportionally, given its actual total size, its iron nickel core is huge. It's too big. And all of there are essentially 2 major hypotheses to explain this. One is that there was a collision early in the history of the solar system, which then blew off the outer layers of Mercury, leaving essentially the inner part of the planet only. And the other idea is that it's so close into the sun that at some point as it was forming, in fact, the sun managed to blow the outer layers off during the formation of the planet. So it's really important to know what the composition of the outer part of Mercury is today. We saw Mercury for the first time with probes about 30-odd years ago, and it looked as though Mercury had the outer composition the same as the white parts of the moon, what's called a northosite, essentially a mineral called plagioclase. And what I've often told you folks is that's essentially the original composition of Coffee Mate. What it says in the press release, in the last line but one, is there are no felsic rocks on the surface of Mercury. In other words, the Coffee Mate ain't there. But it does say there's something else, a thing called basalt. Basalt essentially is what forms most of the outer part of Mars. It's what forms the ocean basins on the Earth. It's a very common rock. But it's a very common rock of the outer parts of normal planets. So, although NASA hasn't highlighted it for you, I'm highlighting it for you now. You heard it here. NASA will eventually turn around and say, you know, there's something really wrong here with the models to explain why small Mercury has this huge core. Any model that says the outer layers of a normally much larger rocky planet were blown away either by the sun or by a collision must be wrong, because the outer composition of Mercury today is a normal composition for a rocky planet. You heard it here first.
Thank you, Simon. Now it's time for me to point out all the fun we're going to have after the meeting. Immediately after this, in the lobby, you'll have caffeine and cookies by Art and Ann Fraser, and this is your chance to talk to our speakers. And I'm sure just with 1 or 2 questions, you could get both Richard and Simon going for hours. So I encourage you to do so. Please note that the rest of the museum is closed. The security guards are still kind of antsy about us wandering around. We want to be nice to the museum, so they'll let us come back and enjoy this room again in the future. Next. Later tonight, if you want to sit down and have some food or some alcohol, we have a standing reservation at the Kelsey's across the street. And these guys look better after a few drinks. Tomorrow, the museum, with our help, has an extensive astronomy day program. I understand that Mike had a lot to do with organizing this. There's going to be 2 talks. First one, Construction of the Heavens by Dr. Michael Hoskins. Michael Hoskins is a Cambridge professor and professor of astronomy history. He's written a number of popular books. I believe Paul Harrison, our president, and Mike Moghadam did a lot of work getting the museum convinced to let Michael speak, because he was originally going to be booked in for like a 5-minute segment here, which I don't think would have been good use of his time. And also Dr. Randall Brooks will talk about Champagne's Astrolab. Next one. Also, there are going to be some daytime displays. The observatory will be open. The RASC will be putting on indoor display. Ron St. Martin will have his meteorites. Chuck O'Day will be showing meteorite impact craters. A big surprise there. And Mike will be manning the booth too. I believe the museum will be using their little inflatable planetarium for those times. Next, please. There's going to be a program especially for kids. I believe we're going to be manning the Ask the Astronomer booth. Is that right? There's going to be a debate for kids. This is like an argument between John Thompson, who will be arguing there is no life on other planets, and Mike Moghadam, who will be arguing there is life on other planets. So I think we should all show up dressed as our favorite alien and cheer when Mike speaks. Also have story time and Cosmic Craft Corner. Next, please. And I consider the best part, except of course it's going to be cloudy for some part of the day, is we'll have solar observing in the morning and afternoon. Now, remember that huge solar telescope that Ken Whitnall brought last meeting? The one that we all drooled over? Apparently he's bringing it tomorrow. Woohoo! And if the clouds are willing, we'll have a star party in the evening as well. Please feel free to bring telescopes or talk to Mike Moghadam if you want to participate more in any of this. The next meeting will be on Friday, June the 5th. And we have one more thing to close out the night, a little bit of dessert. Oh, sorry, before we get to there. I'd like to thank the large crew of people it takes to put on this meeting, especially Chris Tarrant, who was busy working on slides from his hotel room on a business trip, and Tim, who got the audio working today. Unfortunately, he didn't get my voice working.
Extra charge.
Okay, there you go. And to all our presenters. I hope you guys had a good time. We have one more little tidbit. Think of it as a bit of visual dessert. We have this short film. This is a model rocket. It is 36 feet high. It is just a model. It is bigger than my house. It weighs 800 pounds, has a thrust of 8,000 pounds, and was put together by a bunch of amateurs. We think we're geeks. These guys out-geek us by an order of magnitude. Do you want the video? This is, of course, the 40th anniversary of the Apollo launch. Yeah, they used 10 rocket motors. They used, I believe, 1
30 seconds out.
And 9 ends.
30 seconds out from the launch of Stevie's world record attempt, 10th scale Saturn V. This rocket weighs 1,600 pounds. It's being launched on a combination of 8 N motors and 1 central P motor. Expected altitude is between 3 and 4,000 feet. And if Steve is ready, I am ready, Tom's ready, then we're going in 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, ignition!
Wait for it, folks. It's got a good angle.
Alright, heads up. If this rocket comes anywhere near you, stay out of the way.
Probably don't have the wives tonight.
We're at 2,000 feet. We're at 2,000 feet coming down. 2,000 feet. If this rocket gets on the ground, do not touch it. 1,500 feet. 1,000 feet.
Alright, so we can reload and do it again.
Yeah, do it again.
I'm not submitting.